Hello, today we want to talk about intermolecular forces. We will see that intermolecular forces are important in the discussion of many physical and chemical properties of compounds and ions, such as melting points and boiling points, the viscosity of a liquid, cohesion and adhesion forces, the solubility of a compound, the chromatography of compounds, and in more sophisticated applications like the folding of proteins and the activity of drugs. When we talk about intermolecular forces, we need to first determine the Lewis structure of a compound, which allows us to determine the molecular geometry, and based on that we can determine the polarity of the compound. And the polarity then determines which intermolecular forces are going to be active. As we see later, we have dispersion forces, we have dipole-dipole interaction, and we have hydrogen bonding as the main intermolecular forces, and to a lesser degree ion-dipole interactions. We look about dispersion forces. They are a result of polarization of electron clouds by a nearby electric field, and we consider them temporary dipoles. They are relatively small in magnitude. As a result, the interactions between these temporal dipoles is usually relatively weak. Particularly when you look at small molecules and lighter atoms, you have a relatively small interaction. If the size of the atom or the molecule increases, these dispersion forces increase proportionally as well. We also see that open chain molecules have a larger surface area and as a result a larger volume, which makes it easier to polarize them compared to the more spherical molecules. You can see this in the following examples of pentane isomers, where the straight N-pentane has the highest boiling point and the highly branched neopentane has the lowest boiling point of these three isomers. The next interaction we're going to discuss are dipole-dipole interactions. In order for these interactions to be observed, we have to have a permanent dipole moment. This example here shows dimethyl ether, and the structure of this molecule is bent because the oxygen has two lone pairs, similar like in water. As a result, we're going to get positive ends on the lower side and the negative end on the oxygen. As a result, the molecule has an overall net dipole, and the molecules interact then alternating with positive and negative sides due to the electrostatic interaction. Generally, molecules that have polar bonds and an asymmetric structure tend to have a permanent dipole moment. This is where the Vesper rules come in to predict the structure of a molecule. The larger the dipole is, the stronger the intermolecular forces, and this often relates to a higher degree of electronegativity difference. In some cases, like in some benzene rings, resonance can also be a contributing factor to the overall dipole of a molecule. The next force we're going to discuss are hydrogen bonding. Hydrogen bonding is a special form of polarity which involves a hydrogen atom and an electronegative element like fluorine, oxygen, and nitrogen. The bond is highly polarized as shown in this electron map here. And on the left side, the blue part indicates the hydrogen, on the right side, the red part is a fluorine atom. Generally, the positive ends of these dipoles, which is a hydrogen atom, interacts with the negative ends of other dipoles. Usually, in organic chemistry, this is an oxygen atom or a nitrogen atom. The diagram shows the interaction of water molecules, or in this case, ethanol, where the one ethanol molecule acts as a hydrogen bond donor, and another ethanol molecule acts as a hydrogen bond acceptor. On the right hand side, we're also going to see the same kind of behavior for formic acid, where one formic acid molecule is a hydrogen bond donor interacting with the OH group of the different molecule, or alternatively it can also interact with the oxygen of the carbonyl group to form a hydrogen bond. Since there are more than one possibility, the hydrogen bonding in the formic acid is stronger than in ethanol, resulting in a higher boiling point. Hydrogen bonding is also found in many biological systems involving carboxylic acids, amines, amides, and oftentimes these systems form dimeric structure as shown here for the DNA base pairing of guanine and cytosine. There are 3 hydrogen bonds formed. The guanine acts as a hydrogen bond donor for the 2 NH functions and as an acceptor for the carbonyl function. We also know some compounds that can only act as hydrogen bond acceptor, molecules like aldehydes, ketones, esters, ethers, nitro compounds, tertiary amines, and amides do not have a hydrogen attached to an electronegative atom. As a result, they can only act as an acceptor, as shown in the diagram here, which shows the interaction of the alcohol as a donor with an ether as an acceptor. Finally, we're going to address ion-dipole interaction. They result of interaction of an ion with a polar solvent, most of the time water, and the dipolar molecule orients towards the ion, so the negative end of the dipole is near the cation and the positive end of the dipole is near the anion. You see this here for the sodium ion in water, which surrounds itself with the oxygen side of water, and the chloride ion, which surrounds itself with the hydrogen atoms of water. Both of the ions are solvated, and this is why sodium chloride dissolves in water. The strength of the ion-dipole interaction depends on the charge of the central ion, the magnitude of the dipole moment in the molecule in the solvent, and is inverse proportional to the square of the distance. Generally, the enthalpy observation is a good thermodynamic measure for the degree of interaction with the solvent, as shown in the table. You see that the sodium ion, the delta H of hydration, is about 400 kilojoules per mole. The larger potassium ion, the heat of hydration decreases. If you look at the large charged ions like magnesium, magnesium is significantly smaller than sodium, and as a result the heat of hydration is significantly higher. The same applies to the comparison of potassium and calcium, where calcium has a higher charge, is smaller than the potassium ion, and resulting in a significantly increase of the enthalpy of hydration as well. In summary, if we compare all these forces, we see that pretty much every molecule and ion has London dispersion forces. In more specific cases where the molecule has a permanent dipole, we see dipole-dipole interaction on top of that. And the special case of a dipole-dipole interaction is the hydrogen bonding, which is also found in the dipole-ion interaction. If you go from the bottom to the top, you see a significant increase in bond strength when dispersion forces are relatively weak. On the other hand side, hydrogen bonding and ion-dipole interaction are relatively strong. However, we still have to keep in mind that all these forces are generally much weaker than normal covalent or ionic bonds. Let's talk about a couple of examples. We're going to look at the boiling points of hydrogen, hydrogen chloride, and hydrogen fluoride, which are minus 253 degrees Celsius, minus 85 degrees Celsius, and 20 degrees Celsius respectively. So how can we explain this trend? The hydrogen is small and a non-polar molecule, so the dominant forces are lone dispersion forces, resulting in a really low boiling point. In the case of hydrogen chloride, we have a permanent dipole as shown in the diagram, the left side being the hydrogen atom and the orange part on the right being the chlorine atom. We have a medium strong dipole-dipole interaction resulting in a significantly higher boiling point compared to hydrogen. And in the case of hydrogen fluoride, we have a large permanent dipole, and fluorine as oxygen and nitrogen can form strong hydrogen bonding, which are the dominant intermolecular forces here. Ultimately, we see that the boiling points increase from hydrogen over hydrogen chloride to hydrogen fluoride. The next example we want to discuss is viscosity. Viscosity denotes the opposition to flow. Obviously, we're talking about liquids here. We know a lot of compounds which have high viscosities like honey. In our case, we're going to discuss the viscosities of pentane, ethanol, and glycerol. And we observe that pentane has a very low viscosity and glycerol on the other hand side has a very high viscosity. If we analyze these structures, we see that pentane is a hydrocarbon which is non-polar, so the dominant intermolecular forces here are lone dispersion forces. In the case of ethanol, we have a polar molecule that can form hydrogen bonds, and the hydrogen bond formation here is only via one hydroxy group, which makes some kind of interaction of the molecules with each other. In the case of glycerol, we have significantly more hydrogen bond ability, resulting in the ability to form 3 different hydrogen bonds and resulting in a high degree of viscosity. So ultimately we see that pentane has a low viscosity and ethanol a moderate viscosity, and glycerol is a very viscous liquid at room temperature. The next example we're going to discuss is the cohesion and adhesion. Cohesion is the interaction between like molecules. Adhesion is interaction between unlike molecules. Generally, liquids that have a high surface tension also have strong cohesion forces, and they are poor wettening liquid due to the low adhesion forces. So the example we look at here are water droplets. The cohesion causes the water molecules to stick together and form droplets. The adhesion forces in this case cause the drops to cling to other surfaces like glass or leaves, and resulting then staying behind on a plant. The next example is solubility. In this case, we're talking about the solubility of sucrose in water, which is very good, but sucrose does not dissolve in olive oil. So how can we explain this? In order to rationalize this, we need to look at the structure of sucrose, which is a disaccharide formed from glucose and fructose. And we see that this molecule has 8 hydroxy groups and 3 ether groups, which makes the molecule apparently very polar. The 3 ether groups can form hydrogen bond as acceptor, and the hydroxy groups can act as hydrogen bond donor and hydrogen bond acceptor. As a result, this compound dissolves very well in water because it can form a lot of hydrogen bonding. Olive oil, on the other hand side, consists primarily of triglycerides. The R groups in this molecule are long-chain carboxylic acids, which are largely non-polar. As a result, these molecules interact very poorly with sucrose. The next example is chromatography. I don't want to discuss the entire chromatogram here. I just want to look at carotene and lutein, and it turns out that carotenes migrate much further up the TLC plate than lutein. How can we explain this? Usually we use silica as a stationary phase in these experiments, which is considered polar, which means it can form hydrogen bonds with polar molecule. If you look at the structures of carotene and lutein, we see that carotene is a hydrocarbon which has several double bonds but no heteroatoms. Lutein is very similar but also has two hydroxy functions, which makes it significantly more polar. The two OH groups can interact with the polar stationary silica and resulting in a higher degree of retention, or in other words, the carotene migrates more on a polar stationary phase than the lutein. The next example is protein folding, which is obviously very important in biochemical applications. In this case, we see various kind of interactions. So in this case here, we see a carbonyl group acting as a hydrogen bond acceptor and then an H group as hydrogen bond donor. We see a similar picture down here where the OH of the phenol function acts as a hydrogen bond donor and the carbonyl group in a different location of the chain as hydrogen bond acceptor. We see hydrogen bonds between an amide function and an alcohol function up here, and we also see ionic interaction between an ammonia type function with a carboxylate function here, and finally we see what they refer to as hydrophobic interaction, the interaction of different alkyl groups with each other in a long dispersion force. The same thing we see here for two isobutyl type groups here as well. All these kind of interaction give the protein a particular folding, which allows ultimately for the functionality of the protein. The last example I want to discuss is a drug like morphine. When it comes to drugs, it is important to realize that many of the activity relates to weak interactions like hydrogen bonding on dispersion forces or electrostatic interactions. If we look at morphine, we know that morphine is used as a drug for acute and severe pain. Its lowest pKa value is 8, which means that under physiological pH values in blood, which is roughly 7.4, about 80% of it is ionized, which means the nitrogen atom is protonated, like shown in this picture. The drug binds to the mu opioid receptor in the brain via hydrogen bonds on this phenol group, long dispersion forces, which are utilizing the benzene ring, and electrostatic interactions or ionic type of interaction on the ammonium function here. In addition to these kind of basic interactions, it's also important to realize that morphine has a T-shape, which is very, very important as well for the functionality of the drug. If one of the stereocenters has a different stereochemistry or different configuration, the compound does not work as efficiently anymore because the number of interactions are weaker then. In summary, intermolecular forces are important. They're about 1 magnitude less than covalent and ionic bond, but they play a very, very, very important role when it comes to explain properties of solids and liquids. The molecules that only displace long dispersion forces, which are also sometimes called van der Waals forces, are important. They are always present, but often not discussed because they are significantly weaker than the other forces. The molecules that have a permanent dipole interact via dipole-dipole interaction, and the magnitude depends generally on the overall bond polarity. So more polar molecules tend to have stronger dipole-dipole interaction as well, which reflects in higher boiling points and other properties we discussed. And molecules that have NH or OH bonds undergo strong hydrogen bonding, which results in relatively high boiling points as well. Final comments, like always, in order to understand the concepts, make sure you practice, so you get better at it, you see it in different aspects, and you will see these kind of intermolecular forces in many other classes as well, when it comes to practical aspects in the lab, as well as in biochemistry to explain protein foldings and protein structures, activity of enzymes, and other applications. Thank you for watching this video, and like always, until next time, stay safe out there, since we're still in the middle of the coronavirus pandemic.